If I say the word energy, you'll probably think of something like this, our very first invention, making fire. In fact, it was probably the first source of energy that man ever used beyond muscle power. It's not a bad source of energy. It produces heat, light, and even a little bit of sound. But energy is not so valuable in terms of what it is, but rather what it can do for us. So, for example, I can use the energy of this fire to cook my dinner, heat my home, light up the dark, or if I get really inventive, I can use the energy of this fire to help me fly. Hot air rises, and if a bag is light enough, the energy of the hot air will lift the bag upward. It was capturing the energy in fire that enabled the first humans to fly in 1783 in a hot air balloon. The energy of the fire was put to work lifting the balloon into the air. It's a technique that's still in use today. We just have fancier ways of carrying the fire. This is why energy is valuable to us. It has the ability to do work. Fire or heat is only one form of energy. Objects, fluids, and electricity can also have energy, or the ability to do work. Objects when they're moving. Fluids moving like the wind, or falling water all have energy and can all be turned into other forms of energy, such as electricity. You may not think of an object as having energy, but in some cases it can. Take, for example, stretchy materials, like the stretchiness of this bow. When I stretch it, it wants to return to its original shape. So it has the ability to do work, and in a way you can say that it has energy. The work that it does is the work of moving the arrow. But that energy is not released until the bow itself is released, so it can be stored into the future. Likewise, when it delivers this energy to the arrow itself has energy because of its motion. This ability to do work in the future is an important thing to consider because it's a way of storing energy. The elastic properties of stretchy materials is called elastic energy. An object can also have the potential to do work simply by where it happens to be. If it happens to be in a very high place, the object can do work when it's allowed to fall. Since gravity is what makes things fall, and they have the ability to do work when they fall, this potential is appropriately called gravitational potential energy. An interesting thing about potential energy is that it doesn't matter if you raise a piece of steel or water. If they weigh the same and are raised the same height, they have the same potential energy. It's the potential energy of the falling water that is turned into electricity in a hydroelectric dam. Once potential energy is released, it becomes the energy of motion, kinetic energy. The kinetic energy from the motion of this river has done a rather destructive kind of work, moving the buildings off their foundations. The motion of this train gives it the ability to do work, moving just about anything that gets in its way. Electricity is a more common form of energy because we put it to so many different kinds of work, from electric motors and light bulbs to televisions and computers. Electricity also has potential energy because we can store it in batteries where it has the potential to flow at some later time. In fact, voltage is often referred to as potential difference, because it has the potential to move charge from an area of high voltage to an area of low voltage. These forms of energy, elastic energy, gravitational potential energy, kinetic energy, electrical energy, and heat energy are all valuable to us because they have the ability to do work. Looking at it another way, whenever work is done, energy is in use. The remarkable thing about energy is how easily it can be changed from one form to another. For example, solar energy from the sun does work raising water into the air. When water changes to water vapor and forms clouds, the drops gain potential energy as they rise to a greater height. If the drops end up in a lake which is higher than the lake they started in, they now have the potential to flow back down. As the water rolls down from the hills and rivers, it can be captured and stored behind a dam. Later, if it's released, the kinetic energy of the water is turned into the rotational energy of turbine blades spinning in a powerhouse. The rotating turbine turns a generator which changes kinetic energy into electrical energy. The electrical energy can then be used by a device to be put to useful work. In all of this, the total amount of energy that comes out in the end is the same as the amount of energy that was put in by the sun in the first place. This is probably the most important concept in energy, that it can be changed into many different forms, but it cannot be destroyed. That's a hard concept to swallow because there never seems to be as much energy coming out of a system as went into it. That's usually the job of a technician, to find out where the energy was lost. Sometimes it can be lost in ways that you might not think of. Can you see how it's being lost in these systems? If you're going to put energy to work, you need to know two things. First, how much work needs to be done. Second, how much work can the energy do? Well, we saw in our work unit that work is measured in units like foot-pounds, joules, and BTUs. But since energy is nothing more than the ability to do work, it's measured in the same units. So you have foot-pounds, joules, and BTUs. That makes it a lot easier for you. So in this unit, we're going to study different kinds of energy. For example, we're going to study elastic potential energy from materials that will return to their original shape when they're stretched. Then we're going to look at gravitational potential energy, the ability to fall. Next, we're going to look at kinetic energy, the kind of energy that just about any object can have if it moves. And next we're going to look at electrical energy, which can come in handy sometimes, if you're close enough to a radio station. And we're going to look at thermal energy. And right now I'm going to put the thermal energy of this fire to work cooking my dinner. By the way, it was thermal energy in the form of heat loss that was being thrown away in these scenes. It's hard to believe that among the peace and serenity of these mountain peaks, there's tremendous energy. Energy that can be released in a most terrifying way. For people like Ed Rundle, that energy is summed up in one word: avalanche.
I have experienced the potential energy of an avalanche turned into kinetic energy. It has taken me down the mountain about 50 feet. But the time that was probably the most scary was when I had taken a fall a little ways down a steep snow-covered chute, and then an avalanche started behind me and it poured over the top of me. It was pushing very hard at my upper body. When all the action stopped, I was mostly buried, except the top of my body was up in some soft snow. So I was able to dig my upper body out, and the rest of me was pretty much encased in hard snow packed in around me, and it took me quite a while to dig myself out. I was very lucky that I hadn't been turned upside down so that my head was down, or else I would have had to depend on an avalanche beacon or my friends to dig me out, and that could have taken a lot longer, and I could have been injured pretty badly. This particular accident happened to me long before I was a ski patroller, and now that I am, I work with that potential energy with explosives and ski control to release that potential energy, make the avalanche slide. Its kinetic energy does its action without endangering the lives of people or our facilities here.
10,000 tons of snow careening down a mountainside has enormous destructive ability. It can uproot trees, destroy buildings. Why? Simply because it fell from a high place. We don't normally think of falling as a source of energy, but anything that's elevated has the ability to fall back down, thanks to the pull of gravity. If they happen to hit something on the way down, they can do work moving that something out of the way. The ability to do work from falling is gravitational potential energy. Potential energy is energy waiting to be used. The amount of gravitational energy an object has depends on how heavy it is and how far it can fall. It might seem that light objects like a screwdriver would not have much gravitational potential energy, but a high-rise construction worker could kill somebody on the ground by dropping one. An icebreaker, on the other hand, is very heavy, but it's raised only a short distance. The ship rides up onto the ice, gains gravitational potential energy as it climbs higher. That gravitational potential energy is converted to work as it breaks through the ice. Gravitational potential energy is stored energy. Objects have it only by virtue of their weight and their position above some reference point. You can develop a lot of potential energy with a large amount of weight, or with a little bit of weight and a lot of height. Weight times the height gives you the gravitational potential energy. The reference point above which you raise something is usually the surface of the Earth, but not always. Sometimes a reference point could be the height above a single floor. So a person lifting an object onto a shelf is probably more concerned about the potential energy it has with respect to the floor rather than its height above the surface of the Earth, because it's unlikely it'll fall through the floor and reach the surface of the Earth. Although I guess if it was very heavy, it could have enough potential energy to do the work of breaking the floor. This relationship between the height of an object above some reference level and its weight allows you to calculate gravitational potential energy. Weight times height. Potential energy is only half the story in a falling object. When it actually falls, potential energy becomes the energy of motion, kinetic energy. Consider the wrecking ball. When it's on the ground, it has no potential energy because it's not been raised any height. As work is done raising it and it gets higher, it gains, say, 10,000 foot-pounds of potential energy. When it gets to the top, it has lots of gravitational potential energy, but no kinetic energy because it's not moving. Only when it falls and gains speed on the way down does it gain kinetic energy. Finally, at the bottom, it has enough kinetic energy to do the work of breaking the concrete. Notice how the potential energy became kinetic energy, and that the amount of kinetic energy the ball has at the bottom is the same as the potential energy it had at the top. Likewise, the amount of work the ball can do is the same as the work it took to raise it. Since energy is the ability to do work, the mechanical energy is in work units, like foot-pounds or joules. In an avalanche, the weight of the snow increases as the snow accumulates on the peaks, but the height of the snow remains more or less the same compared to the bottom of the valley below. Even though the snow may not fall off the mountain, the potential energy is still there. Gravitational potential energy is a silent form of energy because it's energy waiting to be used at a future time. It's only when that energy is released and turned into kinetic energy that we see how much energy has been stored. Even the ski patrollers use potential and kinetic energy to control the avalanches. The cannon is called an avalauncher and uses pressurized gas to fire an explosive projectile. The gas is stored as potential energy with the ability to escape out the barrel. When it's released, the potential energy of the gas is converted into the kinetic energy of the projectile. That kinetic energy of the projectile is controlled by the elevation and the amount of pressure in the cannon. The kinetic energy of the projectile will carry it to the avalanche site. There's an explosion and potential energy becomes kinetic energy. Potential energy. It can be stored as long as you like. But with kinetic energy, you have to use it when it happens. When it comes to potential energy, liquids follow the same rules. The amount of energy depends on how heavy the liquid is and how far it can fall. Here's another kind of potential energy that can be turned into kinetic energy: elastic potential. When work is done compressing or stretching a spring, the spring has the ability to do work on an attached object, like a valve. Since springs come in a variety of sizes and are made of different materials, they can store different amounts of energy. So every spring is given a value, called the spring constant. Spring constant is a value that describes the stiffness of a spring. A spring constant indicates the force needed to compress or stretch a spring a certain distance. It's represented by the symbol K. So for this heavy-duty automotive spring, K is very high. The kinetic energy of a moving object, whether it comes from the work done by a spring or simply falling from a great height, depends on two things: mass and speed. A hammer is a mass which develops kinetic energy from the speed of the swing. The kinetic energy does the work of driving the nail. As the swing gets faster, the amount of kinetic energy goes up. You could also change the mass, just get a bigger hammer. We'll be dealing with this further in the next program. Kinetic energy, the energy of motion. It can be put to useful work. It can sometimes come from potential energy due to gravity, or from the potential energy stored in elastic materials. But by measuring these forms of energy, we can make sure that they work for us and not against us. vehicle is powered by a quiet, clean, unusual source of energy. Can you figure out what it is? The vehicle makes almost no sound, and when it stops, it actually pumps energy back into its drive mechanism. The secret energy source for the vehicle is inside this black tube. The source is the kinetic energy of a flywheel. If a wheel is massive, well balanced, and spun up to a very high speed, it will tend to keep spinning for a long time. Like an object moving in a straight line which has kinetic energy, a rotating object develops a very similar rotational kinetic energy. It's this rotational kinetic energy of the flywheel that does the work of moving the vehicle. In our last program, we saw how the amount of kinetic energy an object has depends on mass and speed. If you make an object move faster, it has more kinetic energy. And a bigger object will have more kinetic energy than a small one moving at the same speed. In rotating systems, the same holds true. How fast an object spins and how massive it is affects its kinetic energy. Flywheels, which are massive and spin very fast, are being looked at as a way of storing energy. Saving kinetic energy in this way can mean a lot for vehicles that do a great deal of stopping and starting. We saw in the last section how the amount of kinetic energy an object has depends on both its mass and its speed. The kinetic energy of a rotating object is very similar. The speed is an angular speed. It's represented by the Greek letter omega. We've already seen in our unit on rate how to measure angular speed in RPM, or in radians. The greater the angular speed, the more rotational kinetic energy an object has. Therefore, the greater the amount of work it can do. In flywheel drive systems, omega, the speed of the flywheel, is usually very high, storing as much kinetic energy as possible. A transmission taps some of this energy when it's needed and gives it to the wheels. After that, it becomes the kinetic energy of the entire vehicle. Omega. The faster something turns, the more rotational kinetic energy it has. Consider in kinetic energy is mass. But in a rotating object, the shape of that mass also affects the amount of energy that can be stored. Consider the shape of a propeller. It rotates about an axis, with the mass distributed evenly on both sides. As it spins, it has rotational kinetic energy. But suppose the same propellers had a different shape and rotated about a different axis. It would take a different amount of torque to turn a shape like this, so it will develop a different amount of rotational kinetic energy. If the mass is distributed around the edge of a wheel rather than in toward the center, the kinetic energy will be affected again. So will this shape. All these objects will develop different amounts of rotational kinetic energy, even though they all may have the same mass and be rotating at the same speed. This is a problem because you cannot simply use mass to calculate rotational kinetic energy. But there is a term that takes into account differences in shape. It's called moment of inertia. Moment of inertia is represented by I in the formula, and it takes the place of mass. You can even feel moment of inertia with your pen. Rotate it on two different axes, and you'll feel a difference because of the way the mass of the pen is distributed around that axis. The same is true with the tires on a vehicle. When a mechanic balances a wheel, he's showing how the mass of the wheel is distributed around the axis of rotation. If more mass is on one side than the other, the wheel is unbalanced. The purpose of the weights is to make sure that the mass of the wheel is distributed evenly around the axis. If the wheel doesn't have the proper shape, it'll have a different moment of inertia than what it was designed for, and it won't spin properly. The result is the hopping up and down of an unbalanced wheel. Knowing the moment of inertia of a rotating body and its rotational speed lets us determine not only the amount of kinetic energy the object has, but more important, how much work that energy can do. In this case, the rotational kinetic energy of the flywheel is turned into the work of punching the steel. The flywheel takes the work that was put into turning it in the first place, turns it into energy, then returns the work at a later time. The kinetic energy of a rotating object. It depends on how fast it spins and its moment of inertia. With these tools, you can determine how much work that energy can do. Fluids are also able to move at different speeds, so they can develop different amounts of kinetic energy, which can then do work. In this case, the kinetic energy of falling water is turned into the rotational kinetic energy of a generator in a dam. Like objects, the amount of work fluids can do depends on their mass and their speed. Sometimes it's hard to measure the mass of a fluid, especially when there's a lot of it. But mass can be calculated from volume and density. Once you know the mass, you can use the same formula as a moving object. Moving fluids can do work in the same way as moving objects. This water knife takes the kinetic energy of a high-speed jet to do the precise job of cutting carpet. Whether it's moving fluids or moving objects, work is turned into kinetic energy then back to work again. The energy may be turned into several different forms in the process, but if you can measure how much energy went in and how much comes out, you've just found the energy efficiency. And with the cost of energy today, that's an important consideration. After all, we do want to put energy to the best possible use.
So, like, okay already, but who did that terrible thing to me now?
Electrical energy is probably the most versatile and widely used form of energy we have. Its usefulness is mostly in its ability to change into other forms of energy. We change it into the mechanical energy of motors and tape drives, into light, into heat, and into sound. But electrical energy has one big drawback. It's one of the most difficult forms of energy to store. Usually, when we want to store electricity, we first have to turn it into some other form of energy that does store easily. Batteries are stored chemical energy that's turned into electricity when it's hooked into the circuit. The amount of electrical energy that can be stored depends on the amount of chemical energy in the battery. A dam holds water which has gravitational potential energy. We saw in the last section that when the water is released, this potential energy becomes kinetic energy, which can do mechanical work of spinning turbines. That is then turned into electricity by the generator. So in a way, the dam first stores the electricity in the potential energy of water. There are other methods to store electrical energy that are much more convenient than water or chemicals. They don't store for very long, but they're very useful in industry. Sometimes a large amount of charge is needed in a short period of time. Two devices can do this. One is a capacitor, the other is an inductor. Let's look at the first case, a capacitor. Capacitors are sometimes used in starting up heavy-duty electric motors. The capacitor delivers a charge when the motor needs it the most, as it first comes up to speed. A capacitor is a very simple device if you unwrap it and straighten it out. It's nothing more than two plates that are separated by an insulator. The electric charge in this diagram is represented by the plus and minus symbols. Before the capacitor is charged, there's an equal number of positive and negative charges on each plate. A voltage source, such as a battery, does work separating the charges. In other words, it creates an excess of negative charge on one plate and leaves positive charges behind on the other. If the plates are disconnected, the charges will remain separated because the plates are insulated. Since opposite charges attract, they will try to recombine. It took work to separate the charges so they can do work when they come back together. This ability to do work in the future is potential energy. As long as the plates are not connected, that potential will remain. It's much like the potential energy stored in a bow when it's drawn. The amount of electrical potential in a capacitor is called its capacitance. Releasing that potential, like releasing the bow, is done when the plates of the capacitor are reconnected. The charge suddenly flows back and there's once again an equal amount of positive and negative charge on each plate. It's the sudden release of this electrical potential energy that can be used to do the work of starting the motor. Capacitors store electrical energy, but unlike batteries, capacitors release their charge very quickly, rather than over a long period of time. Here's a more familiar use of a capacitor. The strobe light in this flash needs a higher current than what the batteries can deliver. So the batteries slowly add charge to a capacitor. The red light indicates that the capacitor has enough charge between its plates. Hitting the button releases the charge all at once, giving a high current which does the work of making the light. The release of the stored electrical energy in a capacitor is very similar to the release of the stored mechanical energy in the spring of a mousetrap. Now let's look at the second form of storing electrical energy, the inductor. An inductor is another simple device. It's really nothing more than a coil of wire. To understand inductance, we have to look at one of the unusual properties of electricity. Any current that passes through a wire has a magnetic field that appears around it. If the wire is wound into a coil, the magnetic field grows larger because more wire has been squeezed into a smaller space. If a piece of iron is inserted inside the coil, the magnetic field grows larger again. All this simply by running a current through the wire. This is essentially how an electromagnet works. The magnetic field is only there when the current is flowing. When the electric current is shut off, the magnetic field disappears. But a magnetic field is a form of energy, so it cannot just vanish or be destroyed. So what the magnetic field does is turn back into an electric current in the wire. It only happens for a short time, but it is nonetheless a release of energy which can be used to do work. An inductor is like a flywheel which continues to turn after its power source is disconnected. An inductor coil continues to do work for a short time after its power is shut off. It makes sense that if an electric current can generate a magnetic field can generate or induce an electric current. The inductance, or the size of the current that's produced, depends on the number of loops in the coil, the size of the wire, its length, and the type of material in the core. Inductors are most useful as filters in areas where current may fluctuate. This one smooths out the current for a car radio. These two devices are methods of temporarily storing electrical energy. It can be stored on the plates of a capacitor where the charge is separated and has the potential to recombine, or as the potential energy of a magnetic field in an inductor. This is why electricity is such a valuable form of energy. It can change into many different forms, so we can store it, move it around, and use it to do work in a variety of jobs. Heat. It's the most common form of energy around. These thermograms are a special film technique to make heat visible. The colors represent temperature. Red is hot, blue is cold. We generate heat energy to do work, but we also throw tremendous amounts of it away. Every piece of technology that we've looked at so far produces heat, sometimes on purpose, sometimes not. Whenever work is done by a machine, some of the energy to do that work goes into generating heat. The heat may be the result of resistance or the friction of moving parts. In other systems, it could be produced by the electrical resistance in wires. Whenever energy is changed from one form to another, some heat is produced. Sometimes energy seems to disappear, but heat is usually the culprit. Take, for example, the wrecking ball. It's given potential energy. It becomes kinetic energy, which does work breaking the concrete. But suppose the concrete doesn't break. The energy doesn't disappear, it becomes heat. This is why no machine is 100% efficient. The work out is never the same as the work in. Some of that work was lost making heat. Thermal energy is something like kinetic energy in a mechanical system. It's the energy of motion. But instead of the motion of an object as a whole, thermal energy is the movement of the molecules within the substance itself. Just as an object has more kinetic energy the faster it moves, molecules have more thermal energy the faster they vibrate. Thermal energy can move in three ways. The first is when it travels through solid objects. If heat is added to one end of a rod, the molecules at that end begin to vibrate faster. Those molecules transfer some of their energy to the molecules next to them, and so on down the line. This type of thermal movement is called conduction. Conduction, on a microscopic level, is something like this. The only difference is that molecules keep vibrating after they transfer their energy. Some materials are better conductors than others, depending on their molecular structure. Metals are generally good conductors of heat, while wood is a poor conductor. That's why the end of the stick in your hand doesn't get hot when you roast your hot dog. Poor conductors are good insulators, very handy when we want to slow down the rate of heat movement. The second way that heat moves is by convection. Convection is mostly the movement of a hot substance through a cold one and works best in fluid systems. Hot air rises because it's lighter than cold air. It simply floats to the top. This is a serious form of pollution, waste heat. The heat from this stack, along with others like it, can actually affect the weather. After all, the weather itself runs largely by the convection of warm and cold air masses pushing each other around the Earth. The third way that heat can move is by radiation. Radiation is not what goes up in smoke. Smoke is carried up by convection of the hot air. Radiation is what you feel off to the side. It's the one form of heat transfer that does not need a medium. In other words, you would still feel the radiation from the fire even if there was no air between you and the flames. That's how we get heat from the sun. It's radiated to us through empty space. These three methods of transferring heat energy: conduction, where it passes through an object by vibrating the molecules; convection, where a warm fluid floats up to the top of a colder one; and radiation, where the energy travels directly through space, are how thermal energy is moved from one place to another. Heat energy is often used for its own sake, like cooking, but usually it's converted into something else, like mechanical energy. That's how an internal combustion engine works. The thermal energy from the rapidly burning gases causes them to expand, create pressure. That does work moving the pistons. When the pistons move, they develop kinetic energy, which does work turning a crankshaft. The crankshaft gains rotational kinetic energy. It then does work turning the drivetrain and the wheels. The final mechanical energy available to move the car is less than 20% of the thermal energy we began with, because 80% of that energy was thrown away as waste heat. When thermal energy is given to a substance, as in steel manufacturing, the big question is, how much energy do you have to put in to raise the substance to the desired temperature? That can be a rather important question considering the cost of producing the heat in the first place. How readily a substance accepts heat depends on its molecular structure. Every substance has a different molecular structure, so it'll have a different ability to absorb the heat. So every material is given a value called heat capacity. Heat capacity not only determines how much heat the substance can hold, but also how readily it will give the heat back up again when you want to cool it down. Sometimes heat energy is available for free. The Earth has its own heat if you don't mind digging for it. And in some locations, this energy can be tapped and turned into electricity. But this is an unusual case. Usually we get heat by burning something like coal. This is a coal-fired generating station. Can you see where heat is being lost? In the next summary program, you will meet a technician who has to identify the heat losses and calculate the efficiency of the plant. But see if you can spot some of them first. Remember, you're looking for losses from friction, conduction, convection, and radiation. Since we began this entire course, we've been talking in terms of 4 systems: mechanical systems, fluid systems, electrical systems, and thermal systems. But what we've really been talking about are energy systems. In each case, energy is being used to do work of some kind. Energy is the ability to do work. Whether that energy comes from moving an object, a fluid, electric charge, or heat, the value of the energy is in how much work can be done. We most often hear about gas, oil, or the sun as sources of energy, but almost anything can have energy by virtue of its position or its speed. Simply raise something higher, and it has the ability to fall back down. Gravitational potential energy. How much you lift and how high you lift it determines how much energy is available. The how much is the weight. How high is the height above some reference level. When something does fall, it develops the energy of motion, kinetic energy. This energy can be put to work moving whatever happens to be in the way, like the turbines of an electric generator. Anything that moves has kinetic energy. The faster it moves, the more kinetic energy it has. And how big it is, or its mass, will affect the kinetic energy. Even the wind can do it. In this case, the kinetic energy of the wind is being turned into rotational kinetic energy of the windmills. This is how kinetic energy is most commonly put to work, from objects that are spinning. The amount of work a spinning object can do, or the amount of rotational kinetic energy it has, depends on how big it is, but also on its shape. That's where moment of inertia comes in. And since speed is important, we need to measure angular speed. The kinetic energy of a spinning object is one of the best ways of storing the energy of motion. Capacitors store electrical energy by placing a charge on the plates. Work is done separating the charge, and work is given back when the charge returns. Storing electric potential energy in a capacitor is similar to storing mechanical energy in a spring. Its energy is waiting to be released at a future time. The inductance of an inductor coil is similar to the kinetic energy of a flywheel. Work can still be done for a short time even after the power is shut off. Heat energy is pure energy in its own right. It can be moved by radiation through space, by convection through a fluid, or by conduction through a solid. In any case, if thermal energy is going to be put into something, stored there, or even taken out, we need to know how well that object will accept the energy. This is its heat capacity. Heat capacity is something like electrical capacitance. It affects the amount of energy that can be contained. The most important aspect of energy is how it can be changed from one form to another, from potential to kinetic, from mechanical to electric, electric to heat, and so on. But although energy cannot be destroyed, it can be lost, especially when it changes form. Remember in our last program how we asked you to look for energy losses in a coal-fired generating station? For Jerry Allen, identifying those losses is his job.
One interesting point to remember about a coal-fired generating station such as this is that we don't really create any energy at all. We really take one form of energy, potential chemical energy in the form of coal, and convert that to a more useful form, electrical energy, that's more helpful to the consumer at home. This chunk of coal has a heating value of about 8,000 British thermal units per pound. Of that energy, only about 35% of it is actually available as electric energy when the process is completed. The reason for that is that there are several losses that occur in the conversion process. First of all, in the combustion of the coal, approximately 15% of the energy is lost due to inefficiencies in the boiler, primarily due to hot air and hot gases leaving the furnace out the stacks. There are other losses associated with heat radiation losses from the boiler, as well as auxiliary power consumption in the boiler and the steam plant. The biggest loss by far is the energy that's wasted when the steam must be converted back into water. It's an unfortunate necessity of a thermal cycle that we have to condense the steam, but that condensation process and the related loss of energy actually accounts for more energy loss than we send out on our power lines. So the net efficiency of this whole process is approximately 35%. Approximately 15% lost in the boiler or the combustion process, and about 50% lost in the thermal process associated with turning the steam into mechanical energy.
That 35%, by the way, does not include the energy spent getting the coal out of the ground or all the losses in the machines that use the electricity later. Efficiency. The energy in compared to the energy out. It will determine how much work can ultimately be done. Even your body has an efficiency factor. Energy goes in the form of food, but most of that energy generates heat. Only about 10% goes into motion. But knowing that, it's possible to calculate how high you could climb on the energy, say, of a banana. It turns out to be about 45 meters. On the other hand, with about 200 bananas, you could reach the top of Mount Everest. Although you'd be pretty sick of bananas by the time you got there. Energy, the ability to do work.
Right now I'm gaining potential energy. Now that potential energy is being turned into the kinetic energy of my motion. But it's not entirely efficient. Some of it's going into the work of moving snow every time I turn. And some of it's even going into heat. The friction between my skis and the snow is generating a little bit of heat and actually making water. But if you can identify all of these transitions and measure energy efficiency that way, you can put energy to useful work. Or in this case, useful pleasure.
This program was produced at the facilities of Telemation Productions and is part of Principles of Technology, a project of state and provincial vocational and technical education agencies in association with the Agency for Instructional Technology and the Center for Occupational Research and Development, together serving education.